Hello everyone. So in today's video we'll be going over the page replacement algorithm, optimal. Now, in optimal we work forwards instead of working backwards like the other two. First in, that is an E, not an F, first in, first out, and last recently used. Now if you have not watched my videos on LRU and FIFO, highly suggest you watch them as it explains what page faults are and what page hits are, but I'll still give brief explanations of them. So go ahead and starting on the optimal, we have the same reference string as always. This allows us to compare performance, the same amount of frames, which is 3, and we always have that fourth frame that I've made just for us to see if it's page fault or page hit. Now because it is 3 frames, we can fit 3 things into main memory at one time. So that means we can just easily go ahead and write the first 3 just like this, because there's not going to have any conflicts, no issues. So now what we do is we say, okay, yep, they're all page faults, and a page fault is when a new number is brought into main memory. So we go write page fault feature on, and it's represented by a star in pretty much all cases, and H is represented by an H. And it's easy, it's H for hit. And on the next part, which is the 1, we now have to decide which frame is going to be the victim frame. And the victim frame means the frame that will be chosen to be replaced and put back into secondary storage. Now, as I've explained, in optimal we look forward instead of backwards. And I like this approach. So what we do with this is we look, okay, what number is the furthest to the right? So we look at the first occurrence of every number. So we have 7, 2, and 3. So we look, okay, there's a 2. So that's the first one we see. And then now we're looking for the 7 and 3. Okay, there's the 3. Now we're looking for a 7. Sweet. So this tells us that we need to replace 7 because it's the one furthest to the right. Keep in mind, we only look at the first occurrence of every number. We don't look like, okay, there's a 2 there, but there's a 2 all the way over here. Oh, there's a 3 here, it means we replace that. We don't do that. We only look at the first occurrence of the number. So, just going to rub it out so it doesn't confuse you throughout the video. But from that we can tell 7 is the one furthest to the right. Right over here. So we go and replace 7 with 1. So that becomes 1, 2, 3. And that is a page fault because we've brought a new number into main memory. Next we have 2. Now, you might notice that we already have 2 in main memory, so we don't have to do anything. So that turns into the same as before. 1, 2, 3. And instead of a fault, that's a hit, because we didn't bring anything new into memory. Because it was already in main memory, it's called a page hit, because there is not a new number being brought in, because that would be a fault. So now looking, we see, okay, 5 wants to be put into main memory. Which number do we replace? We do it again. We look. Okay, do we see any of the 1, 2, 3s? Yes, we do. Over here's a 3. Do we see a 1 or a 2? Yep, we see a 1. Do we see a 2? Yes, we do. 2 is furthest to the right, so we replace the 2. So that is 1, 5, 3 instead of 1, 2, 3. And that is a page fault. And I find this is, well, you'll find after this video that this is the best page placement algorithm for majority of reference strings because it is really optimal. And that's where the name comes from, optimal. And we're just going to carry on, and I'll explain more of that at the end. We see 3 needs to be replaced. But it doesn't actually, because it's in main memory already. So 1, 5, 3. Now, I always like to add black to show a page hit. So I go, okay, 3 is being requested to be put in main memory. However, we can see it was already in main memory. And I didn't do that for 2, I apologize. Let me just go ahead and circle that there to show that 2 was already in main memory before it was requested. So because of that, we then get our yellow pen out and we write a H showing a hit. So the next number is a 4. And we look and we see, okay, 1, 5, 3. No 4 in there, so we need to do the technique. Look to the right. Do we see a 1? Do we see a 5 or a 3? There's the 1. There's the 5. There's the 3. 3 is the furthest to the right, so we're going to go ahead and replace that one with the 4. So 1, 5, 4. There's a page fault because we have just brought a new number into the main memory. So the 6 is now requesting to come in to the main memory. We don't have it there, so we have to look again. 1, 5, 4. We see a 1, see a 5, and we see a 4. The 4 is the one that gets replaced because it is the furthest to the right. So 1, 5, 6, because the 4 got replaced. So we go ahead and make the default. You might notice some other videos. I like to circle when a number is brought in, just like this. And then I also like to essentially dot out when it gets taken out of memory, just so it's easier to visualize. However, I don't think that is necessary. We don't really need that because this algorithm is working forward. We're not looking backwards, and that's why I do all that in the previous video. That's why I record when a number's brought in, because the last two algorithms, they look at when a number's been brought in or used. So back to normal, we look and we see, okay, a 7 wants to be brought in. We have 1, 5, 6 in main memory. We see the 1, we see the 5, and we see the 6, because 6 is the furthest to the right. We're going to go ahead and get rid of the 6. So 1, 5, 6 turns into 1, 5, 7. Once again, that is a page fault. And here we will notice that a page hit occurs because they are requesting 7 be brought into main memory when we already have it in main memory. So we just go ahead and we write the same as before, as nothing has changed in our main memory. And because we don't have a new number in main memory, it is then a page hit. Now you will see it's requesting that a 1 be put in. Same scenario as before. We already have a 1. And that shows that it's not, once again, a page hit because we don't bring new numbers into the main memory. It stays the same. 1, 5, 7. Something you might already be noticing is we're getting a far lot more hits, and we're already halfway through. We've got more hits. We just passed the halfway mark, and we've already got more hits than the first in, first out algorithm, which had the most hits. And that's great. The more hits we have, the better the algorithm is for this reference string. Because the more hits we have, the less time the operating system has to take swapping out victim frames. So if we carry on, we can see, okay, there's a 0 that needs to be replaced in because there's no 0 in our frame. But we have a look and we see, okay, here's a 5. So that's the 5. Which one's next? A 1 or a 7? And we will see that the 1 is next. Right over there. And as you can see, 7 is not present at all. And when 7 is not present, it means it won't be used again. So we can go ahead and choose 7 to be replaced because we're not going to use it again, right? So I'll go ahead and just minus those. So 1 and 5 is kept, but 7 is replaced as it won't be used again. And that, as we know, is a page fault. So over here we see a 5 is wanting to be put into memory, but we already have 5. So we go overlook there. See, 5's already in memory, so we can't bring in a new number because it's already there. So 150 stays as 150, and that is a page hit. I mean, if you already look at this, you can see you already have 1, 2, 3, 4, 5 page hits. So we can already see this algorithm's working really, really well. Moving on. It's looking for a 4. So what we do is look what's already in our main memory and we see there is no 4. So we have to have a little scan. Okay, 1 we see is over there. 5 we don't see. 0 we see. So that means we can replace the 5. So we do 1, 4, 0 opposed to 1, 5, 0. And just like before, that is a page fault. Now, it gets trickier the closer you get, and I'll explain why. So, we're looking to replace one of these with a 6, and we see that we have 1, and we have 0, but we don't have 4. And when they're number, when the number we are looking for, so 4 in this case, is not there, we see there's not 4, it means that it won't be used again. And if something's not going to be used again, that means it's completely fine to get rid of it, because we're not going to have to swap it back in. So we're going to get rid of the 4 and replace it with a 6. And it creates another page fault. Now the reason this gets complicated for people, because a lot of people ask, what happens if 2 out of my 3 numbers aren't there? Then you can choose any number. You can replace the second one, or you can replace the third one. And we'll see if we have an example here. So 160. You can see same scenario as before. The 0 is here, 1's here, 6 is not. So we do 1 and the 0, they stay, but the 6 gets replaced by a 2. So we do a page fault. And here we want to add a 3 in. And we can see once again the 0 and 1's there. But 2 is not. So we can replace the 2. So 1 and 0 stay the same. 2 turns into a 3. And once again, we already have a 0 in the main memory. So we can circle that 0, show that it's already in main memory. And from that, without even writing anything, we can tell it's a hit, because we know from that what's in main memory is not going to change. And you can see that's going to happen again next time, because there's already a 1 in memory, even when it's requesting the 1 to be put into memory. It's already there, which causes another page hit. And as we know, the more pages we have, the better. So that is 1, 3, 0. And if we just have a look at this, we can see just how good the optimal algorithm is. I mean, it's in the name, it's optimal. It is a really optimal algorithm. And we go ahead and count now. We got 1, 2, 3, 4, 5, 6, 7 page hits. 7 page hits. And we know that our reference string is 20. So it's 20 long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Reference is 20 long. So in the exam or test, they're going to say, how many page faults did you get? I have not seen any exams or assignments that ask how many page hits you got, but they might ask you that. And for the page faults, it's simple. We have 20 reference strings. And for the 20, we got a total of 7 page hits. That means out of the 20 reference string, we got 13 page faults. And that's how you would answer the exam question for optimal. Now, looking at the last 3, because this is the last video, I'm going to add an extra part comparing the performance of optimal, first in, first out, as well as last recently used. So, optimal, we got 13 page faults. That is optimal. For last recently used, we got 18 page faults. And keep in mind, these are all for the same reference string. And for first in, first out, we got 17 page faults. As you can see, they're both very similar. Both of these last recently used and first out work very similar ways, with a small change. But from this, we can see that the best algorithm for our reference string, which is this, is going to be the optimal. So I hope that helps. If anyone has any questions, anyone has any ideas for the ways I can present my videos better next time, or any feedback, I'm happy to take it and to make my videos better. Thank you for watching. I hope I've answered all your questions. And like and subscribe if it really helped you, to stay notified for the next video updates. So thank you so much for watching my video. I really appreciate it. I really appreciate the support. Enjoy the rest of your day.